Lesson 5.2, Bisectors and Triangles. When we start this lesson, it says a sporting goods company has 3 stores in 3 different towns. Here they are in this map. They want to build a distribution center so that the distance from each of the stores is the same. So this moves, and you can manipulate this. You're trying to figure out where this distribution center should be so that it's equidistant or the same distance from each of those 3 stores or those 3 towns. So how good do you think your guess is? And what you can do is there's a little click right here. You can click and show. It will show you your distances, and you can see how good your guess was. The next part of the same question, you're going to do this, but notice the measurements change. Is there one spot? Is there more than one spot? And we're going to ask, what do you think is the quickest way to find the middle point without using a graphing calculator? Mathematically, there is a way to do this. So how do you think it could be done? Concurrency. We're going to talk about concurrency. And honestly, points of concurrency is where all the points come together. So it's 3 or more lines come together to make one point, I should say. So it's where several lines or intersecting rays or segments come together into one actual point. So it says the perpendicular bisectors. Keep in mind, perpendicular bisectors. Here's an example. This 5 and 5, that means this J to P, that's the bisector. It cuts it perfectly in half, 5 and 5. Perpendicular intersects at a 90-degree angle. So these perpendicular bisector. So all 3 sides of the triangle have been bisected at a 90-degree angle. So it says the perpendicular bisectors of the sides all intersect. So look at these kind of orangish lines or segments. They all come together to one point. Well, that one point is the concurrent point or point of concurrency where they all come together. And look at these blue numbers, 5.45, 5.45, 5.45. What that means is that when the perpendicular bisectors come together and make that one point, it creates equidistance or equal distances from this point of intersection to each of the vertices. So no matter how I move this triangle and manipulate it, these blue lines are always going to be the same because the perpendicular bisectors come together and they create a point equidistant from each of the vertices or the vertex, the corners of the triangle. So there is a proof for this one. We're not going to go through the whole proof, but there is important vocab. So I kind of said this, but concurrent, it says when 3 or more lines intersect at one point. So when there's 3 or more lines or rays or segments, they come together. They're called concurrent. And that actual point is called the point of concurrency. And sometimes there's special names for those points, and sometimes there aren't. In this case, there is. We'll talk about it in a second. But basically, it goes through, this is the midpoint of each side, and it's perpendicular, 90-degree angles. And it goes through the whole proof showing that if you have perpendicular bisectors on all 3 sides of the triangle, then it will create distances from that point of concurrency to each of the vertices, and they'll all be the same. And you can go through this on your own, but basically it is just explaining or showing with a kind of like a step-by-step proof what I was just explaining. So point P is the same distance from A, B, and C. So let's try this. We're actually going to do this. If you have a compass and a paper, you can do this on compass and paper. In fact, I recommend getting used to those. If you don't have a compass and paper, it's not a big deal because you can do this online. So it says, create triangles, acute, right, and obtuse. Do one of each if you can, and do the perpendicular bisectors. So I'm going to start with a triangle, and I'm not going to make it super big. We'll go with an obtuse triangle. Okay, so you make this shape and go from each 3 points and then go back to the original. And then I'm going to take a compass, because remember the compass, when you go from each point, make a circle and do that exact same circle on the other end point, make another circle, and where they intersect, that creates the perpendicular bisector. So hopefully you can visualize this as I'm doing it. Here's my compass. I'm going to go from this intersecting point to that point. There's my circle. I'm going to do it again. So I'm going to go from this point to that point. So I have 2 congruent circles going from each end point, and I'm using that left side of the triangle. So this last segment from endpoint to endpoint. Now I'm going to make a line from the two intersecting points of the circle. So I'm going to go from here across to there. So I have that one segment on the one side has the perpendicular bisector. So that line that I just drew is the perpendicular bisector. You want to do that to all three sides. Now, technically, you only need to do it to two because they will intersect, but I always recommend doing it to the third side as well, because what if you were off on one of those? But if you do all three, then you're like really for sure confident. All right, because it's sometimes hard because there's all these things here, I'm going to highlight all the purple stuff and I'm going to hide it just so it's out of the way. Hide. There, now I can just look at the blue. And now I'm going to go with the compass. And every once in a while, you just don't know until you try. So I'm going to start here. And there it goes. It went to the right spot. There we go. Now I have the two congruent circles on that right segment. And I'm going to take my line from the intersecting points of the circles. Notice I'm not paying attention to the triangle. I'm paying attention to the circles. And I'm going to highlight all those. And I'll make them a different color just so they're not the original blue. I'll make them green. And then I'm going to go back and put back my hidden objects right here. And let me hide all the rest of the circles so you can only see the lines. I'm going to hide those. Oh, I'll just unhide everything actually. Unhide. And then I'm going to hide these circles. Hide that circle. There we go. Hopefully you can see the green line and this purple line. They have a point right here. Now that point is the point of intersection where the two perpendicular bisectors meet. I could do the third side, which again, getting good practice. The smaller your triangle is on the computer, it's doable. But on paper, the smaller your triangle, it actually makes it really hard to use the compass. But on a computer, it's okay. Okay, so you can do it to the third side. Because it's on the computer, it makes it a little bit difficult because of all the tiny drawings. But you can do this on paper. I would actually draw this bigger and do all three sides if I was using an actual compass. Okay, so let's just check this answer. And I don't want to check it on the video because it's going to give you some of the answers that you want to see. But it shows you the difference between an acute triangle, a right triangle, and an obtuse triangle, how this point of intersection or point of concurrency changes depending on the shape or the size of the triangle, like acute, obtuse, and right. Okay, so let's investigate this. It says, how can you construct a circle that contains the three vertices of a given triangle? So we're talking circles and a triangle. So if I find the perpendicular bisector of all three sides, it actually creates a circle. So let's just say this is the point of concurrency. See how it's equidistant from each of the vertices. And I do this, the perpendicular bisector is not shown, but they are here. They're right here, here, and here. That is actually the point or the center of a circle that goes around the triangle and hits all three vertices. It's equidistant from the vertices. So these from here straight out, these orange lines, each of those are a radius. So it's a radii, plural for radius. So it says all points on a circle equidistant from this point or the point of concurrency. That point's name is the circumcenter. It's a circumscribed circle. It means around or outside. So circumcenter is the actual point. Circumscribed circle means a circle around the triangle. So let's manipulate this. And you can drag and move this. So if I move these points of the circle or of the triangle, look how the circle changes. Look how the point changes, this circumcenter. It's not even in the triangle anymore. So mess with this and kind of manipulate and see what happens inside the circle, outside, or outside the triangle, inside the triangle. And notice the circle always touches all three vertices of the triangle. And then it's basically asking you to describe what happens if it's an acute, a right, or obtuse triangle. Like, what do you notice about that circumcenter? And now we're going to actually use it. So I have a city manager who wants to place an emergency siren. So it's the same distance from schools, hospitals, and recreation. So rec center, the hospital, and the school. So we need something equidistant from all 3 points. Notice 3 points. Think of a triangle. And you're going to actually figure out what we just talked about with the circumcenter and the circumscribed circle, the same distance, because a circle is all the points equidistant from any one point. So think of the center or the circumcenter, and all the points around it would be a circle around those 3 points. So the solution's here, but I want you to try. How would you do this? Now, my hint to you would be start with 3 points at those 3 places. Draw a triangle. Hopefully you have straight lines. Draw a triangle and do exactly what you would have done to find the circumcenter or perpendicular bisector of all 3 sides. Go ahead and try that. All right, here's an actual part that says, try it. If a city manager decides to place the siren, how can she actually find the location? So instead of doing it, you're going to describe it word for word so that you know later on when you have a test or a quiz, you can refer back to how do you actually do this? How do you find a point equidistant from 3 other points? Now we're going to do concurrency or point of concurrency for angle bisectors. You have to know the difference between these. So the perpendicular bisectors, which is kind of confusing, the perpendicular bisectors cut the sides perfectly in half at a 90-degree angle, but they're equidistant to the corners or the vertices. The angle bisectors cut the angles in half, each of the angles, but then they're equidistant from each of the sides. So it's kind of opposite of what you think. So manipulate this a little bit and see how those blue lines, always identical, the angles are always perfectly bisected. And it's creating those blue lines that are equidistant to the sides, not the angles anymore. So they're equidistant to each side. So let's look at what this does. And this one, again, like kind of describes what you can do or how to do it step by step. And I'm going to just talk about the vocab. So if you have the point that is equidistant from each of the sides, it creates an inscribed circle. Inscribed meaning inside the circle and like basically skimming each of the sides of the triangle, like not going outside, just barely touching one point on each side. And it's from creating the angle bisectors. Okay, and that point is actually called the incenter. So the incenter is a circle inside or inscribed, and it's the angle bisectors. A way to remember that, which might be kind of cheesy, but the angle bisectors, that's a vowel, uses the incenter and it's inside or inscribed. So those are all vowels. Angles, inscribed, inside, incenter. Whereas the perpendicular bisectors, that's a consonant, perpendicular bisectors are circumscribed, outside, like on the outer, circumscribed, and they're circumcenter. So those are perpendicular bisectors, and they start with consonants, if that helps. All right, so again, a manipulative. So go ahead and manipulate this and see, no matter what you do, acute, obtuse, if it's right, notice the incenter is always on the inside. It's a circle inside the triangle, so it can't go outside the triangle. It's inside. And notice that these 3 radii, or the radius of the circle, that is the distance to each of the side lengths. And you're going to describe how you can do this. Like I would do a step-by-step instruction for yourself so that you remember later on when we have a test or quiz, how do I find a location on the side of each triangle that's equidistant? And it's the incenter, finding the incenter. So here's to identify and use the incenter. We're going to use some algebra here. It says QP, so QP, this distance right here, and RP, this distance right here. What is the radius? So notice these are angle bisectors. So if it's angle bisectors, then that's creating, I'll just draw here, that's creating the incenter. I'm not going to draw this perfect, but you get the idea. So you have this ugly circle on the inside, which if this is given, the 3x plus 1, and this is given 5x minus 3, those are both radii. So set them equal to each other. So I'm going to show you the solution. It even tells you, hey, they're the angle bisectors, therefore the segments are the same, and set them equal to each other. And it shows you step by step the the equation, you distribute that 3, you move the x's to one side, you solve for the variable x, but it does not ask you for x. It actually asks you for what is the radius. So what is this actual length? Once you find x, then you plug it back in. And I would plug it into both of these. So 5 times 3, since that's what you got. 5 times 3 minus 3, see what you get. And then 3 times the quantity, plug in the x, 3 plus 1. If you do not get the same answer for both of these, something is wrong. And then I would say to start over again. All right, there's a try it. And the try it is very similar to what we just did. It says use the figure shown. The measurement of BAF right here is 15. Well, notice the markings. If that's 15, then that means this side is 15. So each of these are 15. Okay, 15. And then it says the measurement of angle CBF right here is 52. So if that side's 52, this side would be 52 because they are angle bisectors. And hopefully you know, okay, well, what do I know about triangles? All the angles in a triangle should add up to 180 by the triangle sum. And so the question is, what is ACF? ACF right here. But whatever this is, this will be the same. So I want you to think if you had all 3 angles in a triangle, the measurement of angle A plus the measurement of angle B, like the whole measurement, the whole big angles, and the measurement of C should equal 180. Well, you have it broken down. You have 15 plus 15 together, that makes angle A, the whole one. So you'd say 30 plus, add these 2 together, that would be angle B, and then you need to find angle C. Once you find angle C, cut it in half because it's bisected. And then it has another one. So these are algebra skills. If you need help with algebra, please do not hesitate to ask. All right, bisectors in triangles. Properties of the bisectors. This is a concept summary. So instead of having like rules, it's basically showing you with manipulative. So here it is, perpendicular bisectors. And these are things I guarantee are easy to forget. So you might want to write them down, put them in your notes because these will show up again. So perpendicular bisectors create this circumcenter, the point that creates a circle that goes around or on the outside of the triangle. So the circumcenter is the point and it's equidistant from the vertices, and it's called the circumcenter. So you can manipulate this and mess with it, but basically the bottom line is, it's kind of cool, that each of these orange perpendicular bisectors create equidistance distances to each of the vertices or each vertex. And then the other is the angle bisectors. Again, I would recommend you write these down. Angle bisectors create the incenter, the point on the inside that creates an inscribed or an inside circle. And it's called the incenter. It's equidistant from each of the sides. And again, feel free to manipulate these. Notice each of the angles is bisected. I hope this helps.